Let's talk about outliers. We talked about them briefly a little bit ago, but an outlier is a piece of data that's significantly different than all the others. Here's two examples of scatter plots. Here's an example of an outlier. It's significantly different than all the other points. This one over here is not an outlier because when you look at the overall trend of your pattern of your data, you're going up as you go to the right, and the one at the top right kind of falls in line with the rest of your data points. Is it farther to the right and up? Yeah, but it still follows in line there. However, when we look at our trend over here, we go up and go to the right. This one here is nowhere near the line. But as a side note, we would call this point up here influential, but not an outlier. Here, an outlier is significantly different, is significantly lower than all the other points. So once again, here we have the number of beers divided by their weight and the alcohol level. Once again, we also now have categorical on here with male and female for representing different symbols for our points. Here we have an upward trend. We have this one female up here, significantly different than all the other data, but still falls in line with the overall trend, so it's not an outlier. Taking a look down here, though, this one does not fall in line close to that overall trend right here, so therefore, since it's significantly different, we would call it an outlier. The one up here would be considered an influential point. Now, let's take a look over here. Here we're looking at IQ scores versus your grade point. Well, I would say the overall strength and direction and shape, I would say it's linear. Is it a strong linear relationship? No. But is it linear? Yes. As you go up, as you go to the right, there's a definite pattern. We do have a couple of points that are a little bit different. We have this one here, and we have this one down here. I mean, this one here is somewhat different too. But these 2 points do stick out. So our overall shape, we would say, is linear. It's a weak linear, but it's positive association. Now, what's going on with these 2 points? Well, for this point here, it's above average IQ, but they're not performing well. In other words, we're probably going to say they're probably lazy or have a lot of stuff going on at home that's affecting their grades. This one here has a very low ability, but is working their tail off. And so they're putting a lot of effort into it, and that effort is allowing them to be able to survive and get it okay grades, even though their ability is very low. So now let's take a look at your correlation coefficient. Your correlation coefficient gives us a numerical measure for strength and direction. Now, when R is positive, it's a positive association. When R is negative, it's a negative association. Meaning, if it's positive, your graph goes up as you go to the right. If R is negative, it goes down as you go to the right. Now, you should recognize some of this. This right here is really your z-score formula. In this case, it's a z-score of all your y's. This is the z-score of all your x's. So you got to figure out the z-score for your x, the z-score for your y, multiply them together. Do that for your next point, z-score of the x, z-score of the y, multiply that together, do that for your next point, and so on. And then this says add them together, and then divide by 1 less than the number of data values. Needless to say, this is not something we want to do by hand. We want to use our technology to do this. Now, as you take a look over here, we have our pulse rate versus our swim time. It's definitely a negative association because as you go to the right, you go down. As we look at our z-scores here for the y's and the x's, remember our z-scores do not have any units in them. So this has no units times something that has no units, which means your R would then have no units. So R is unitless, meaning no units. You can only find R when you're dealing with quantitative data because you don't have means and averages when you're dealing with categorical data. So that's another reason when we're dealing with scatter plots, we're only dealing with quantitative data for our axes. Now, we talked about this before, that you have your z-score for your x's, z-score for your y's. So remember, your z-score just tells you the number of standard deviations you are above or below. Well, in that situation, changing your unit should not make a difference, because remember, this has no units, this has no units. So if you change your um, units on either your x's or your y's, doesn't make a difference. It's not going to change the way R is calculated. So once again, we're looking at the number of standard deviations to the right and to the left of 0, where 0 is your mean, and you're looking at the number of standard deviations above and below for each one of your points. Then you want to add all these z-scores together. Now, just a second here. Now, for the most part, the husband's age and the wife's age are typically somewhat similar. If we did a scatter plot and calculated their correlation, it would probably be about a 0.94. However, if you're looking at the heights, they're not necessarily always related. Some of you might think that taller women like to date taller men. That might be true. Shorter women might want shorter men. But that doesn't necessarily hold as true as it is for the ages. So that's why your R ends up being smaller. So let's go ahead and try to calculate R. We're going to use your calculator. Now, to use your calculator, there's going to be one thing you're going to have to do first. This first thing you'll have to do once, and then you should not have to redo it again unless your calculator gets reset. So we're going to go Second, Catalog. We're then going to go ahead and hit D, which is your X to the -1 button. We're now going to go ahead and arrow down to Diagnostics On. We're going to then hit Enter on that, hit Enter a second time. It looks like it does nothing, and that's okay. We're not concerned about that. But now it's going to give us the information we're looking for. So now we're going to go ahead and enter our data. So we're going to hit Stat, hit Edit, arrow up to get rid of our data, hit Clear, do not hit Delete, hit Clear, hit Enter. Now we're going to type in the first number in each parenthesis. We have a 1, we have a 2, we have a 3, and we have a 4. We're now going to arrow over to the next column, and we're going to type in the second number that shows up in each parenthesis, which is a 2, a 4, a 5, and a 6. Now that our data is entered, we're going to go ahead and hit Stat to calculate R. We're going to arrow once to the right, and then we're going to go down to number 8. Number 8 is linreg A plus ABX, which is a little bit different than number 4. And now we end up getting R. In this case, we get R to be a 0.9827, blah, 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 blah. Your calculator does a great job of crunching numbers for you so that you don't have to. We're going to be using our calculator to calculate R instead of trying to do it by hand. So once again, when you're dealing with your correlation coefficient, the units does not make a difference, because your Z for your X's and the Z for the Y's undoes all the units. So the units does not make a difference whether it's minutes or hours or seconds or whatever. So keep that in mind. Now, it does not distinguish between the explanatory and the response variable, because here's your explanatory, here's your response, but it's being multiplied together. And remember, you can multiply in any order you want, so these two could be flipped, and you're still going to get the same answer. So here's an example of where we flip our horizontal, our response, and our explanatory variables. Your graphs are going to look a little bit different. However, when you calculate R, you get the exact same R, even when you flipped your explanatory and response. So keep that in mind, that changing your explanatory and response makes no difference. Once again, R has no units. We've talked about that before. Your values for R always range from a +1 down to a -1, and it can take on all values in between. If R is really close to 1 or really close to -1, it's a strong relationship. If R is between 0 and 1, it's a positive relationship. If R is between 0 and -1, it's a negative relationship, meaning if it goes down as you go to the right. Now, we had said if R is close to 1 or -1, it's a strong relationship. So hence, if it's closer to 0, it's a weak relationship. Here's an example where R is 0. Here's an example on the right where R is a negative because you have a somewhat downward pattern, but definitely not real strong. It's fairly weak, so therefore R is somewhat close to 0. Here's another downward one, but definitely closer than the one above it, so it's closer to a -1. Here's an example where it's really close to a -1 and your points are really close to a line. So here's a positive association that's still relatively strong. Here's another positive association, but somewhat weak. Notice you're at 0.5. Typically, I would say if you're at a 0.55 or 0.6 for your R and below, then it's going to be somewhat weak. And the closer you are to 0, the weaker it is. Then here's an example where we're looking at our R values again. So here's your R values. You're negative, so you know your R is going to be negative because you're going down as you go to the right, but it's somewhat spread out. However, when you look at the one below, our R is definitely higher, and it's not nearly as spread out from a line that would cut through the middle of it. So it's a much stronger relationship, so therefore our R is closer to a -1. Now, R only works with linear data. R does not work with nonlinear data. So R would work great for this first one. But here, this is not linear, it would not work well. This one over here, it's not linear, so you cannot use R to describe what's going on. Now, you could go ahead and transform your nonlinear data into a linear data set using logarithms, but that's not in the scope of this class. We are only going to be focusing on what comes to you as linear. We also have influential points, and then we have outliers. Now, keep in mind that if you go ahead and change one point into an outlier, your R can definitely change. Your R uses averages and standard deviations. Both are influenced by outliers. So if I go ahead and take this one point up here and slide it way down here, my R goes from this value to this value. Definitely got a lot less. So here's another example of an outlier, a point going from up here, way down here, and affects R. Let's take a look at this here. We have 3 points. Let's go ahead and show, just a second here. Sorry about that, I wasn't seeing R right away. It's right here. It's really close to a +1, but if I take this point here and move it up here, just moving that one point, we now went from a +1 down to something that's negative and close to 0. So moving this point around really changes the way that R is. Now we're pretty close to a strong one again because it's pretty close to 1. So just moving this point up or down really makes it weak or strong. So keep in mind that an influential and outlier point really makes a difference.